You guys going to do a lab today, and what you'll do, I'll just get a basic synopsis of this here in a second, but you're going to find a molar mass of a liquid. But it doesn't stay a liquid at a hot temperature. So basically you're going to take a pipette, in fact 3 of the pipettes, okay? And what you're going to do with those 3 pipettes is you're going to fill them with a liquid. It's called a volatile liquid. Okay, what's a volatile liquid? It just means it evaporates pretty fast at room temperature. And if you raise the temperature hot enough, it all evaporates. So you're going to put liquids in here at the bottom. And what you're going to do is you're going to heat those liquids up. On the outside is going to be a hot water bath. And you're going to put it in a boiling hot water bath. And it's going to cause the liquid inside here to turn to a vapor. Okay, so it's going to turn into a vapor. You're going to leave it in there, give it a long enough time to where it gets rid of it goes from the liquid to the gas, and it's all a gas. Then you're going to take it out and you're going to let it cool. Well, that vapor, once it cools, is going to go back to the liquid form. But you're not going to have as much as you did before, because the rest of the stuff is out in the air, and it won't come back in. Only air will come back in. Okay? That stuff, the liquid's already out, that's formed into a gas. So what we're going to do is we're going to find, experimentally, the molar mass of 3 different things. The 3 different things, and you guys will just do 2 of the 3 in your groups, and we'll divide them out. So what you're going to do is find the molar mass of ethyl alcohol, acetone, and isopropyl alcohol. So those are called volatile liquids because they evaporate pretty fast. Some of you know why they evaporate fast. It has to do with intermolecular forces of attraction. So there's this equation on the front side, and it says PV equals nRT. You guys have used that. And you guys are like, yeah, we know that. We know how to use that. Pretty good at that. You can solve for T and N and P and V. Then you're given some more information. It says N is equal to the mass divided by the molar mass. So the M stands for the mass of the liquid, or mass of the gas, not the liquid. And then capital M is the molecular mass of the gas. So if you take mass divided by molecular mass, what do you get? Moles. So what you do is you substitute this in right there. And you say, okay, PV now equals little mRT over capital M. Okay, so now we can solve for a liquid, and we can kind of see, we can identify a liquid by doing experimentation of a volatile liquid. So that's what we're going to do. Well, that's what you're going to do. I'm not going to do it. And you can switch this equation around to solve for molecular mass. We're going to do that here in a second. We have some sample data. Down below, we got a pre-lab question. We're going to use that. And then by doing that, you're going to be able to solve your problem after you get your data. So, methyl alcohol is being used. So methyl alcohol was placed in here. Okay? And it was heated up to boiling water, which is a 99.5. It won't boil to 100 because we're higher altitude. So you'll have to use a thermometer to measure the water's temperature. Okay, it should be around 98, 99, but you know, maybe a half a degree here or there is probably not going to have a big play on our problem and our calculation. All right, the pressure in the room was 738, a little higher altitude, so it's a little bit less. We turn the page over. It says the temperature of the water bath is 24 degrees Celsius. Okay, that's not important other than knowing the density of water at that temperature. So at 24 degrees Celsius, you can look up on a table the density of water, because the density of water changes due to whatever temperature the water is at. Okay? Or room temperature water bath would be. And so then you can take the temperature of that, and then we can get density table and you can figure out what that is. So we have to finish filling out this data table. Okay? So we're not going to spend a lot of time doing this, but the mass of the empty pipette has to be subtracted all the time because we don't care about its weight other than it's something that holds our substances that we're testing. So it's 1.557 grams. We're going to let you guys, there's two balances that go out to the thousandths of a gram. You need to use those on this experiment. Okay? Next one. We have the mass of the pipette and condensed liquid. So that's after you've heated it and let it cool in the room water temperature. So that's after you put it in there, you heated it, you take it out, you put it in the room temperature, and now it condenses back down into a smaller volume. Okay, that we can weigh out. Okay, what is that? It's 1.5, it's gained a little weight. Not much. As you can see, it hasn't gained a whole lot. So it's really important that you, when you reweigh it, that you dry the outside, okay, really good. You don't have any condensation on the outside, and it's completely the way it was when you measured the pipette empty. Okay, so here's the deal. Mass of pipette and water. On this part, I don't think I'm going to have you do it. I'm going to do that for you. Because I think what will happen is they're all going to be really close to one another. So I'm going to do that one for you. But it's 16.001 grams. Okay? So then, what is the mass of the condensed methanol? You guys figure that out for me. What is it?
0.014.
0.014. Good. These two subtracted one another. Okay? Volume of the pipette. So this is the mass of the pipette in water. Okay, so the volume of the pipette, mass of pipette in water. So we have to subtract out the pipette, right? So go ahead and do that.
Wait, which one are we doing? Are we doing mass of water and filled pipette or doing?
Yeah, mass of water and filled pipette. So mass of water. So what's the mass of the water? I wrote these out somewhere, so I made sure that I have them down. So, all right, where are my answers? Did you get it?
What are we supposed to be subtracting?
Got to get the pipette mass out of there. So you guys subtract the pipette out. I think I can find what I did my work on. Did you guys get it? So it's just, yeah, what is it, 14? 444? Yeah. All right. The volume of the pipette. Okay. So this is the mass of the water in the pipette, and we know the density of water is 0.9973 grams per milliliter. So here's the grams of water. I want to know the volume of the water. And I want it in liters, since it's going in the ideal gas law. Okay, so I need to know the volume of, basically I need to know the volume of this that my gas is in. I need to know the volume of this. Okay? Get it? Yep, I want it in liters. So it should be 0.0.
145.
Yep, 0.0145. Okay. Now I've got my equation, and I should have all my values. So PV equals little mRT over capital M. So I got to solve for capital M. So capital M equals what?
Little mRT over PV.
Yeah, little mRT over PV. Okay? So now, do you have the mass of your gas that's condensed now into a liquid? 0.014. The R value has to be in millimeters of mercury because that's what the pressure is on the front side. It says it's 738 millimeters of mercury.
Isn't that like 63?
Yep, that's 62.4. So R is 62.4. The temperature has to be the 90, can't use the room temperature water, has to be the 99.5 because that's the temperature of the gas. So the temperature of the gas, when it's in that hot water, would be 273 plus 99.5. So go ahead and plug that in. So you got 0.014 times 62.4 times 372.7. Right? Okay. The pressure is whatever it is, barometric pressure, 738. And the volume is right here, 0.0145 liters. So doing all that, you should get the molecular mass. Okay, and then your answer you come up with is 31, right? Is that what you guys got?
I got 30.4.
Did you get 30? You get 30.4?
Yeah.
Okay. And that would be grams per mole. The actual answer is whatever the formula for methanol is CH3OH. So let's go ahead and calculate what the actual molar mass is. Okay, so we're off by 2 grams. And if you wanted to find your percent error, you take 2 divided by 32 point. It's supposed to be 32.04, right? That's what this is. 32 point, actually 32.05 is what it is.
That's what I was reading.
Yep. But anyway, we can have you guys find the percent error. That's what you're doing. So you already know the setup once you get to your final answers and you can do it. So let's look at,
How do you find the percent error again? Is it
you would take the
which
difference
first? Like,
in your two values.
theoretical minus experimental or
Yeah,
experimental?
doesn't matter because it's an absolute value because the percent error, whether it's negative or positive, you're still off that percent. And then you just divide by what the actual is, okay?